read all safety guidelines for your test equipment and wear personal protective equipment when using electrical testers. In order to review basic oscilloscopes before starting with the Industrial Scopemeter, I have 3 circuits set up: AC resistive, AC capacitive, and an AC inductive circuit using a program called Multisim, which we use to simulate electronic and electrical circuits. Each oscilloscope will measure the current and the voltage. The current will be represented by a red trace on channel A and a blue trace on channel B. We are using a current probe attachment with a scale of 10 to 1. So whatever current is read in here in the circuit or measured in the circuit, it puts a signal out, and that signal is voltage to the oscilloscope that represents a scale of 10 to 1. So 1 amp will be 10 volts. Okay, keep that in mind. So let's run the circuit. First, let's check the current. We have about 3.55 amps RMS. This is an RMS measurement. Okay, when I open up the oscilloscope, you're going to notice 2 traces. The red trace is current, the blue trace is voltage, and they are both nice and clean signals. There is no distortion in those signals. All of these circuits, these 3 circuits, are linear loads. There's no distortion in the signals. Now, on a vertical scale of an oscilloscope, so this is part of our review, the vertical scale or the y-axis, you are looking at signal level, and it's represented by volts per division. If you want to change the scaling on that, down here you adjust that level or that scaling by changing the volts per division. And channel A and channel B are independent of each other. So you can look at 2 different traces. Okay? Across the oscilloscope screen, you are measuring what's called period. And period is measured in time per division. So each one of these divisions is a set time, and you can adjust it by adjusting the time-based scale. Just set it to 1 millisecond per division, so I'm basically zooming in on one small part of the waveforms. Okay, it affects both channels when you adjust the time base. Okay, so voltage level on the vertical scale, the y-axis, and time level on the horizontal or x-axis. Okay, so I'm going to close this, and before I do that, I just want to say that the current and voltage are in phase. What do I mean by that? Well, if I were to draw a line through the 90-degree mark on the current signal, it would line up exactly at 90 degrees on the voltage signal, so they are in phase. Let me close this. Now we're going to look at the capacitive circuit. Do you think they will be in phase? And if they're not in phase, what will be different? Let's have a look. So you'll notice that the current is ahead of the voltage. Why do I say ahead? We just discussed time or period is across the oscilloscope screen. So when I move across the screen, I hit current, then I hit voltage. Current, then voltage, current, then voltage. It is leading. The current is rushing into the capacitor ahead of the voltage because it appears to be a short. Yeah, it charges up, then the polarity changes, and then it drains. Okay, so it does it on the opposite side. All right, so the current leads in a capacitive circuit. Now let's look at the inductive circuit. In an inductive circuit, what do we have? We have voltage, current, voltage, current, voltage, current, because we know that we have a time base or a time per division across the screen. So current lags an inductive circuit. And this is a problem for power factor. Why is it a problem for power factor? Well, if I stop this At this point, let's say the blue trace is negative and the red trace is positive. The red is the voltage, the red is the current, the blue is the voltage. You're not making any power at that point, so you start to affect the power factor when you have a lot of inductors in the circuit, or if you have too many capacitors in a circuit, you can have that same issue. All right, so you can notice I'll set up the 3 different scope meters and you can see the different signals. I don't know if I can overlay all 3. Yes, I can. And that is the result of having capacitors and inductors in the circuit, and you can only see that with an oscilloscope. You can determine the phase angle between the two, and then you can correct it using power factor correction equipment. So I'll close this up and we will move on with the industrial scope meter exercise. I'm going to use a 125B industrial scope meter. It's a Fluke product, and I'm going to measure current and voltage in an AC circuit similar to what I did in the simulation. I like to do this before doing any harmonics measurements. I like to get a visual of what's going on in the circuit and get some values. The setup that I'm going to use is down, excuse me for 1 second, I think it's on page 16 or thereabouts on measurements. So the setup I am going to use is setup number 2, and there will be a voltage probe on channel A and a current probe on channel B. And I just want to explain something. That little alligator clip and little J loop of wire that connects into that lead, you can either use it or you can use the common jack in the center. They are the same polarity. It gives you the option of using this little jumper lead with the alligator clip, and then the signal is shielded within that lead, and that is why they do that. As with the simulation earlier, you will see 2 traces on the screen. A red trace for channel A and a blue trace for channel B. And I will set them up, channel A for voltage and channel B for current. Okay, so what we're going to do, we're going to power up the scope and we're going to reset it back to the factory. If you're ever working with these things and you run into a real problem where you get stuck, you get backed into a corner, you may have to reset it. So I hold the menu button down. You won't be able to see me do this. And hit the power button and we are reset. You'll notice that we just have channel A active now. We will set that channel B active in a couple of minutes. First, you need to go over your probes. It's very important to know your probe polarity. So we have current probe and then we have our voltage probe. Now the voltage probe, whatever conductor you connect that to, you have to pay attention to which way the current probe is pointing. You'll notice there's an arrow on the inside of this current probe. Whatever lead you connect or conductor you connect the voltage probe to, the red one, this must point to the load, and I'll show you what happens if you don't do that. Also, we have a scaling switch right here, and right now it's set to 10 millivolts per amp, which is the 40 amp scale. There's a 400 amp scale also, so pay attention to that. So things you think about. So number 1, polarity with respect to each other, and I'll show you what happens when you miss that. It's very, very important when you're working with 3-phase power equipment. You may have 3 voltage probes and 3 current probes. You need to make sure they're all polarized correctly, okay? Okay, now I have the current probe connected and the voltage probe connected, and we can see that we have 242 volts RMS on channel A. So what I need to do now is activate channel B. So we have to go into the scope meter menu and we have to click on measure B, and we're going to set it to amps AC right here. And you can see there's a lot of other settings that we can select. So I'll hit enter, and it's going to ask us about our probe sensitivity. We are set, that little switch I showed you, 10 millivolt per amp. Click done, and now we're set up. Now, 242 volts RMS, 6.85 amps. Now, you'll notice that the two waveforms are separated quite a bit, meaning that the zero line for the blue waveform, which is the current, is down where my finger is here. You'll see that little blue rectangular block. And the voltage, the center line for the voltage waveform is up here. Now what they do is they separate those for you so you can find your traces, because sometimes they're laying on top of each other. So what I'll do is I'll move B up to match A. So the two center lines will be on the same plane. Okay, oh, I overshot it. Come back down a little bit. So now we have a nice waveform for our current and our voltage. What I will do now is I will reverse the probe, and you'll see what happens. I have now reversed the probe, so you can clearly see that the voltage and the current are out of phase with each other. This is a common mistake when you're doing power quality measurements, especially like I said earlier on three-phase systems. You will, your readings will not make sense to you, so you have to make sure that you're polarized properly. And this is why I do this, is I like to get a visual of my current and voltage waveform, and they talk about this in some of these manuals. I'll go into the scope meter. I set up measure B, and I tell it to look for angle, or what's known as phase. So I'll go down to phase, I'll set it to phase. And it's telling you that it's 180 degrees out of phase. Okay, that is incorrect. Okay, so we need to fix that, put it back, make sure they're phased correctly before you do any power measurements. And again, that's why I said I like to get a visual of what I'm doing before I do my power quality measurements. Now you notice that the phase angle between B and A is 0, and that's because this is a purely resistive load. I'm actually measuring a heater, so that is correct. Now we are going to get a visual on an AC drive, so a non-linear load. I'm going to start it up. You're going to notice something completely different. It's ramping up. It's connected to the same 240 volt source. Now you'll notice that the waveform looks really thick and noisy, and what we can do with that is we can go in and we can apply what's called smoothing. So if I hit the scope meter and just scroll down to the signal type, and I can enter smoothing, and we can get a clear view of the waveform. And you can notice that the current waveform is fairly distorted. So then in the next video we're going to measure the current harmonics and how much of that harmonic component is made up with the different subcomponents, like the 3rd, the 5th, the 7th, the 11th, which are very common, and so on. So we'll do that in the next video.